All right, there you go. Thank you, Lee, and take it away.
Great. So apologies for that, folks. So as I was saying, I'm the technical lead of the Penny Lane ecosystem here at Xanadu. The ecosystem itself, as I was saying, was kind of comprised of these three individual packages right now. So the programming front end and overall framework, which we express everything in, is Penny Lane itself. You can find the repos on GitHub. You can go to the website and see that this is all fully Apache 2.0 open source. So do as you see fit. Next on the list is our compiler and execution runtime, Catalyst. So from Catalyst, the goal here is to actually do quantum program optimization as well as classical program optimization, generating our binary payloads and making sure that everything is as we expect, ready for running on a given hardware backend. So the flow of information goes from Penny Lane to Catalyst. Catalyst does its optimizations, and then next on the list, if we want to do some HPC-focused simulation, we have our Lightning suite, right? So the Lightning, as well as just what we're using right now as a way of giving people the ability to kind of hit small to medium scale, qubit workloads. We can go up to the 40s of qubits on HPC machines, but I think the most important thing right now is actually the compilation itself. Understanding, getting ready for fault-tolerant quantum computing machines, making sure that we can target specific gate sets, looking at the optimizations of those specific programs, and understanding the resources required for executing a workload. So, what are we trying to solve really here? I think the idea is, making sure users, a user being a researcher, somebody who wants to play around with these things, somebody who has a business case, they have the ability to declare whatever their intention is in a programming framework. It doesn't matter what their intention is. We want to give them the ability to kind of express in what way works for them. And once they have their intention declared, we should be able to capture that intent with a given representation of the program. So I know I mentioned, Penny Lane itself is Pythonic, and I know the word Python tends to give shivers in people from the HPC community. However, Python is just the way to express the intention here. I'll talk a little bit about compilation of that in a few minutes, but really giving people as easy as a way to kind of declare what they want to run, how they want to run it is important. So the idea here is once we have this captured representation of a program, we should be able to kind of transform it again, as one expects in a compilation flow, from high-level concepts to low-level physically backed quantities, right? So if a user declares, I want to run an algorithm, well, we've got to map that algorithm to what a hardware platform will support. What gates does it support? What type of interactions are allowed? What is the flow of data throughout that system? The lowest level program then should be executable by the hardware system, and ideally the workload you have defined at the high level should be fully represented at the low level for execution. Whatever that means, the interplay between devices and how that works is a very important quantity to be aware of. And lastly, the most important thing is you have to get your results back. We can do whatever execution we want. If we can't pull the results back, there's no real utility here. So having the ability to pull results back and do transformations necessary that map back to what the user requested is an important concept to have here. All right. So in our ecosystem, this is kind of how it works. So our front end layer, as I said, is Penny Lane, giving the people to express what they want to run. Next on the list for compilation, we have Catalyst, which is the compiler suite. Next on the list for runtime and hardware execution, we have Catalyst, which has a runtime and as well as ties into some hardware devices that we can focus on. And lastly, the kind of post-processing classical layer, which is the Penny Lane Pythonic front end. We integrate with JAX, the numerical library, NumPy, API compatibility, as well as with Catalyst, so that we can kind of talk all the way from the bottom up to these guys. Okay, so next, what constraints should we be aware of? I think there's a few that are always important when you're building out an ecosystem. And the first one is making sure that development happens at the right layer of abstraction. For algorithm developers, we don't want them to be worrying about RDMA over some specific link. We don't want them to have to be caring about understanding the intricacies of C++ code. And they want to be able to express what they want at a high level in a way that we can take and map it to the right layer of complexity for execution. So then the next problem here is how do we expose flexibility in this way, so that making sure that we can actually take these high-level concepts that are easy to use and not burdening them with the complexity of what needs to happen to it. So this is kind of another thing we've been trying to solve in the ecosystem. Next on the list, scaling up and scaling out is a big one, right? So, I think most of us here are aware that, once these machines are, fault tolerant ready, we're going to have a lot of large scale problems to solve, solving very large workloads, solving very large data sets, solving very large, modes of execution. These are kind of things that need to be, considered all the way through here. I think, the NISC era has been very much a starting point for people, but, NISC era thoughts don't work in a fault tolerant world. Next on the list, I think it's relevant to hear, where do HPC systems sit in the mix of all of this? How does that type of ecosystem work with all of the above? All right. So this is kind of a very brief, very quick and dirty overview of like abstraction layers in a fault-tolerant computing stack. And this is mostly just from the perspective of compilation itself. So a user defines their application. This is captured into some representation. We can do transformations on. We then do some logical decomposition on this. We then do some logical optimization on this. So we get to, a target agnostic gate set so that one can actually express this in a way such as Clifford plus T or Pauli-based computing modes. But the idea here is we can understand high-level resource counts, resource estimates, mapping things that are interoperable across platforms in a way that we can share information flow inside and outside our ecosystem. So next on the list, obviously, once you go beyond the logical layer, we want to go through error correction. We want to map this through for execution with an error correcting optimizer, optimizing pass ecosystem. Obviously, handling the encoding itself, mapping it to the computing model of the hardware, and then lastly, getting to the layer of like hardware level encoding. So what instructions do we want to execute on the platform we've built out? So lastly, once we have the binary itself, this maps the co-processors, control systems, whatever is needed to make sure that the quantum computer itself does the things we expect it to do. All right, so this is kind of a long-winded walk around that I'm going to come back to the start and just discuss the front end. So our front end here, as I mentioned, was Penny Lane, and this is kind of the early quantum programming paradigm. So in Python, you write your instructions, you say, hey, I want to declare this device, I want to generate these gates, I want to do an expectation value at the end, and I want to build some cost model from the output of the quantum execution. Right. So I think traditionally we're all kind of familiar with openQSE as kind of a serial list of instructions, or at least more recently with the ability to have some structure in there. But this human readable format really, it's nice as an idea of a starting point, but we have to kind of move beyond this as we start scaling problems. And so this is kind of where I want to get into the program capture problem. So taking what a user writes for their program and capturing that intention in a way that is, not human consumable, but consumable by a compiler, consumable by an optimizer, consumable by something we can do easy transformations on to make our program map to hardware as we need to. Okay, so there's two kind of approaches here. I'm not expecting you to read the code on this one, but the idea is you have AST parsing, which is kind of a deep embedding model of an EDS of a DSL. So you express everything to be done, the abstract syntax tree in whatever language you're using here of choice. You need to express all quantities that you want a user's program to be represented. You have to handle everything yourself manually, and it becomes a little bit burdensome in the long run if you want to expand things out. So the one on the right, which is shallow embedding, or what we call tracing, is the approach we've taken in Xanadu. So we have this decorator called QJIT, and the whole idea of QJIT itself is its focus is capturing the essentials of a program. So here's kind of a very simple quantum program. We have a Hadamard, we have some Pythonic math expressions, we have some JAX functions, and the idea here is not everything here needs to be represented in the captured program itself. Obviously, we want to have anything we define, such as the quantum programming instructions. So in this case, qp.hadamard, we want to make sure that's executed on the hardware. Well, the math, exponential call, do we care about that call being part of the program? I would say no. Do we care about the output of that call? Absolutely. So what happens here is we have kind of a dual tiered approach that we execute this function in its entirety, and then we capture the pieces of it that are necessary to represent our program itself. And so those captured pieces get tracked into a given program representation that we care about, and then we do transformations on that program representation. All right, so what does this look like in the wild? Okay, so we do this kind of by tying into JAX. You get all the NumPy functionality and some of the SciPy stuff out. Oops, let me go back. Sorry, you get some of the SciPy stuff out of the box. Oops, I've gone too fast, too far. We have this program rep which they use, which we can tie into. We can easily register new data types, and we can build custom lowerings all the way down. So I say, JAX with an asterisk here because this is kind of a starting point to have a good tracing infrastructure. The JAX team have put a lot of work into making this, interoperable with many ecosystems, and we can nicely extend their ecosystem to work with ours. So how does this look in the wild? If we take a quantum program on the right, which is a Q node here, just defining this is the thing we want to run on the hardware platform. We have a for loop in there, given the number of wires. You can think of wires here as qubits. And we have RX gate in a loop. And in the old openQSE style way of doing things, we have this unwrapped loop represented in this capture program on the right. You don't have to worry about all the words in here. You can just see that there's a lot going on here. And we're repeating this RX multiple times in a serial list on the red line arrow. But what we actually want is we want to be able to capture that for loop itself. So making sure that we can capture the for loop, we can capture the branches, we can capture all of the structure of the program itself. It helps us to keep the overall program size bounded. And a bounded program size is necessary for us to actually do optimized compilation passes on it in the long run. There's a very just easy graph to see here, right? If you have capture, if you have a serial, lines of code increases with serial, lines of code remain bounded with capture. And if you're trying to make your compiler efficient and fast, you definitely don't want to be doing passes on 10, 20, 30, 40, a million, 10 billion lines of code if you can represent it with 10,000. So why am I talking about this? For FTQC systems, structured programs aren't a want, they're a need. This is an absolutely essential paradigm we see internally, that one cannot do the type of workloads we will want to care about without having a good structured program representation. This serial approach has been good now, but it no longer fits the bill as we start scaling up. We need loops, we need control flow, we need the ability to have arbitrary functions and subroutines. We need to be able to do data analysis. We need to carry metadata, and all the things we haven't even thought about yet to make sure that our program is fully expressible and transformable and analyzable as it flows through our compiler ecosystem. So as we make smaller programs, we can do easier transformations on smaller programs, and then we can do faster iteration on the R&D necessary. And our overall ecosystem, we like MLIR, right? I know like the LLVM ecosystem is a bit of a behemoth, and MLIR, for those of you who are not familiar, is a way of building compilers within the LLVM ecosystem. It's tough, but it gives us a lot of power and expressivity for tying into classical and quantum hardware platforms. We also have this XDSL ecosystem as well for rapid prototyping in Python, and I'll discuss both a little bit further. All right. So next on the list, I've talked about the front end, why we want structured programs, why we need them, and once we have them, well, what can we do? We need a compiler, okay? So I kind of like this quote that Rob Souter was kind of talking about recently, that compilers are some of the most complex programs ever developed, right? And realistically, having dealt with the inner workings of LLVM recently, I can definitely say I feel that pain a little bit, and it's absolutely necessary that one bears that in mind, that the compiler is one of the most important pieces of the ecosystem, and working on this is something that requires kind of an all hands on deck approach to make sure we can kind of do this in the right way. There's obviously this paper discussing on the importance of quantum intermediate representations. This is a nice article where they discuss the idea of like having this IR based approach where one can map a program to and then do transformations on it. So what does our ecosystem look like? This lovely blob of boxes on the right is kind of where we are right now. So the front end, which is Penny Lane, with the NumPy API provided through JAX, we allow kind of a dynamic programming model where you can define everything you want in Python. You can define, custom operators, custom instructions, and we capture this program by this tracing mechanism that we have adopted from JAX. And once we have this tracing mechanism in place and the trace program is ready, well, we can hand off the program to the compiler. And so with that, we go to the MLIR ecosystem. The MLIR ecosystem is a way of kind of expressing different things we care about in different manners, such as dialects, which is kind of the language of different, you call it the language, I guess, of different ways of representing quantities we care about. So HLO is kind of this high-level optimization mode that was popularized by TensorFlow. We have gradient dialects to handle, backpropagation and autodiff, how we handle control flow, how we handle linear algebra. All of this is expressible with the language that is provided to us with MLIR. So we can tie in here, we can extend the framework to suit really whatever we want. We also have the ability to kind of inject and work with other compiler ecosystems in this way. And I will mention Jeff on the side here as a way in here. Lastly, once we have the compiled program representation, my slide updates, there it goes. We have the ability then to take this binary output and then do device, like when I say do device, I mean handle device host interactions, do real-time classical post-processing and pre-processing, and then handling the overall execution of the workload. So there's a lot of pieces here. I'm going to mention a little bit on the Catalyst dialects. So as I said, the dialects in MLIR are kind of the language we want to express for given quantities we care about. So Catalyst has multiple different dialects, quantum operations, gradients, error mitigation, quantum error correction, penalty-based computation, the openQSE model for photonic systems, even ones for ion traps and real-time IO ops. And the nice thing is here, it's fully expressible. You can kind of add whatever you care about. You represent the instructions you care. You get data flow and analysis out of the gate. Constants, data can be attached in a nice way to the ops. You can kind of declare properties you care about, as well as having a nice C++ base class to kind of enable the transforms. Did I hear a question? No, sorry. Okay. So what does a Catalyst program look like? So this is what MLIR really is. It's just a bunch of high-level functions that your program that you've defined in Python gets mapped down onto. And we have setups and teardowns. We have entry points for the program. We have arbitrary quantum kernels, which map the workload we care about, as well as any transformations we want here. So the nice thing is we can hold all classical and quantum instructions that we want to run on a system in this program. And that includes any type of hardware we care about that is necessary for that execution. So code gen, I know not everybody wants to hear about code gen from compilers with LLVM, but I'll keep it brief here. So the idea is once we define our Python program and we get into MLIR, we can do transformations in whatever way we want in MLIR. And after those transformations have been applied, we can go then to the remaining pieces to the LLVM dialects. So LLVM IR itself is the kind of de facto standard for building hardware compilers. And the way we have this expressed right now is we can compile our entire pipeline to LLVM IR. And with that, we have the ability to compile for, classical codes, for quantum codes, to kind of use as a way of keeping all of the components we care about interoperated within the same, let's say, payload. We fall down, we generate some ELF files, we link them all together into a shared library, and then that shared library is something we execute with Catalyst runtime. So I'll keep it brief on the idea of what actually we expect to see with compiling with real world applications. So this is kind of a one we were looking at, just as a test bed of the compiler, taking a high level workload that has nested control or nested for loops, nested control flow, adaptive measurement outcomes, all the pieces we care about having in a given program representation. And starting at the, I'm going to say that the top of the labels to the bottom of the labels is progressive lowering through the compiler stages of the stack. And you can see the gate count is kind of going up as we're doing these transformations. So the main thing here is we can express high level algorithms that a user cares about, and then we progressively map that to something that is hardware compatible for a given system we wish. Obviously, once you kind of go beyond 50 qubits, classically intractable is the word that people tend to use. Obviously, if you have enough money on hand, you could probably go up to mid 50s, but beyond that, really, you're not really getting much benefit at all for trying to execute any of this classically. The main thing we care about here, though, is understanding that stress testing of the compiler is absolutely important. As we start scaling up for fault-tolerant workloads, the compiler ecosystem itself is going to be a potential bottleneck. And this is the picture on the right, or the picture on the bottom, let's say, the peak memory usage. This is our compiler trying to compile this program as we're increasing the number of qubits for the application. You can see we're already at like about 40 qubits or 40 gigs of usage for a 51 qubit problem. And so if you want to scale that up, you can understand very quickly that one needs to be aware that compilers are potentially a bottleneck that we will need to solve as part of this targeting the hardware system itself. All right, we're just at about the halfway point, so I think I'll try to speed run a little bit through on time, so there's plenty of time for questions. Once we're kind of at the outcome of our compiled program, well, we can just have a runtime library that provides stubs that we can link against for execution. So if you have a given hardware platform that's exposed as a C API, we can just call into those stubs for your given platform. So if I've compiled, all the way down through the given workload, I want to kind of run a bunch of quantum gates, Pauli X, Hadamard, S, gate, ORX, whatever you care about here is held in the program representation. And then your system linker for your hardware platform will provide the definitions of those. And so that gives us the ability to kind of decouple the compilation from let's say, what one needs to build out in the runtime in the hardware. Obviously, taking observables into account, returning different quantities of interest, whether it's expectation values or probabilities, whether we want to do gradient-based workloads, we have full freedom for this with our stack. And how this looks in practice is something like the following. So we get the LLVM IR, which is kind of defining the quantum stubs we care about targeting. We do cogen for the given platform we're running on. We have a runtime API which we link in, which calls this device interface. And then depending on which devices are available in our runtime, whether it's the HPC devices, whether we can still output openQSE if we want to send it to something like Bracket or another platform that doesn't provide support for structured programs. The QPU directly can be targeted in this way, or third-party simulators. The nice thing as well, we can do classical cogen as part of this. So we're not strictly just compiling for the quantum instruction set, but because we can maintain the full classical code in the program as we're lowering, we can target CPUs, GPUs, TPUs, whatever you want, as long as it's expressible within the LLVM ecosystem. So that is kind of a whirlwind tour of our ecosystem. And I think the next thing I want to really touch on is tooling interoperability. So there was a lot of moving pieces there. We're aware of how complex an ecosystem this becomes pretty quickly. But one of the important things is we all need to be figuring out how do we keep all of this talking nicely together. So I mentioned MLIR. We like MLIR, but I'm aware not everybody is willing to kind of invest the effort needed to get that up and running. It's a very heavy build system. There's a long build times. It is quite challenging to configure out of the box. Not everybody is a fan of C++. I have we work with a lot of people who come from a C background or even a Fortran background who will say are not a fan of template metaprogramming. Versioning, compatibility, conflicts, this is a standard fare in the LLVM ecosystem. If you want to keep things moving, sometimes you're going to have to update a lot of codes to make sure that things are interoperable across the ecosystem. You can't really do much modification to it at runtime. This is kind of you build once and then you use that infrastructure for whatever you're trying to do. I think most of the domain scientists we've spoken to have said, this is definitely not something they will want to interoperate with. So the idea is how do we make it easy for them to kind of build
technology. To talk to you about our project, which combines generative AI tools with quantum-inspired algorithms to help developers get the most out of these new technologies.
What? Sorry, there was something going on there. Okay, I'll continue. A lot of the compiler concepts, are challenging for domain scientists to learn. It's tedious when you generate large amounts of IR. So, if you grow your program significantly with lots of transformations and passes, things can get pretty out of hand in terms of memory usage and as well as compile time. One of the main things here is one compiler framework for everything is unrealistic. We're definitely in the opinion that having one vendor-controlled compiler ecosystem just doesn't make sense. We want everybody to be able to use whatever makes sense for them to express their workloads, but to at least allow some form of interoperability with other tools in the stack. So one of the first things we started looking at was XDSL. So this is a Pythonic implementation of kind of MLIR as an ecosystem. So the idea is, if you still want to define transformation passes on a program, I want to look at how do I, do merge rotations on specific gates, or how do I take a specific quantum, templated pattern that I know can be stenciled throughout the code base, and I can collapse it to one instruction. You don't want to write that in C++, perfectly fine. You can write it in the Python layer in XDSL, and our ecosystem should allow the ability to inject this into our ecosystem. The next thing on the list is Jeff. So Jeff is kind of this interoperability format which we've defined with a bunch of others for making compilers talk together. So the first thing I'll talk about a little bit is XDSL. So this kind of solves the issue of, I want to spend that time writing or expressing my intentions without learning how I build stuff with the MLIR ecosystem. So it's a very nice project. It's, I think, supported by University of Edinburgh and potentially University of Cambridge in the UK. We work very closely with the teams there on making it so that our ecosystem allows one to interoperate and define passes in XDSL that can be used by our compiler infrastructure. So how does it work? Well, you can prototype your passes, and then you can port it directly to the MLIR framework itself. Sure, running Python code is going to be slower, but if it takes you 2 days to write a compiler pass in XDSL instead of 2 months in MLIR, well, writing it in XDSL, understanding what works, and then porting it to MLIR is really the approach we want here. And even internally, we've had a lot of the research teams who are already looking at using this to kind of help speed up their research. So how do we avoid reinventing the wheel here, right? Like, as I said earlier, that expecting one compiler to do everything is unrealistic. Every vendor knows their hardware best, and we shouldn't be injecting everything into one compiler ecosystem. I just don't think it scales well as a model. We like C++ and MLIR with a Python and NumPy front end. Maybe some of you like Julia or Haskell or Rust or even Fortran better. And we shouldn't be kind of stopping anyone from working in that framework. You can pick whatever you want and define what works best for you. Forcing everybody to a single domain-specific language or framework really isn't the approach, right? People should work, again, in the way that works best for them, whatever that needs to be. And lastly, well, this is why we created what I call is Jeff, right? So the Jeff framework here is kind of a partnership between multiple organizations and research groups. This is fully supported by the Unitary Foundation, or hold on, there we go. So yeah, the Unitary Foundation on GitHub hosts this. It is us, the ticket team at Continuum, the Unitary Compiler Collection, many other research groups working to kind of provide a neutral ground for having compilers work together, right? So I define passes that you want to use, great, we can interoperate with Jeff. You define passes I want to use, great, we can do the same thing again. And so, like, one of the main things we wanted to kind of achieve with this is, well, avoiding the, defining hard APIs. We want things to move fast. We don't want people to be blocked by standardization. The motivation doc here kind of sets it up that this is a moving standard. We don't want everybody to adopt it. We just want to provide a way that we can all organically define, update, expand, and use this in whatever way makes sense for us. Further development happens in the open. We don't have, progressive meetings to figure things out. We just discuss it on the fly and figure out what makes sense, make a PR, make an update. Anybody is free to jump in here to do whatever you need in your ecosystem. So, talk is cheap. What do examples look like? So on the left is an example of, don't worry about the code, but it's just a big block of the MLIR dialect from a quantum program that we get from Catalyst. On the right is what happens when you use Jeff to convert this to Continuum's ticket ecosystem and looking at the output from that. So, this kind of gives us the ability to interoperate our compilers in ways that really isn't available in many other frameworks at all. And, you can optimize it in there, make it smaller, and then we're free to pass it back. At the bottom, you can kind of see that these examples are already checked into the Jeff repo. So I would say if you're interested in kind of compiler interoperability, you want to get more involved in this, feel free to kind of jump in and start opening issues in there to do whatever makes sense for you and your ecosystem. All right, so I think I have about 5 minutes left. So I'm gonna, before I start taking questions, I'm gonna say, where's the HPC? I've talked a lot right now about our ecosystem, our compiler framework, interoperability between things, but I haven't really talked much about HPC. So really, this is the approach we're taking here, right? That the quantum computer is the HPC. The HPC components are inside it. We don't really see this as a separate entity. We see it as one all-encompassing solution, that we need full stack quantum computing, which has HPC in there in the list, okay? So the important things here, we're all really building these multi-device heterogeneous systems with programmability at every layer in the stack, right? From high-level expression all the way down to controlling things across PCI Express, you know, across UA-Link, across whatever type of bus architecture we have available to us. You know, some of us have FPGAs for fast error correction, need at least 1 microsecond or less, you know, ability to go back and forth between executing layers. The ability for kind of having CPUs for on-device execution of the program, as I mentioned, this control flow, branching, all of that needs to be intermingled with the quantum execution to make sure that things work well. Obviously, you know, compilation has to happen on the CPU too. Making sure that GPUs, you know, NPUs, et cetera, anything can be used for what I would call low latency to differentiate it from ultra low latency in the 1 to 100 microseconds regime. Some of these things might be useful for some platforms who can handle a little bit more latency. Some of these are not useful for all platforms who need really low latency interconnects. But figuring out how do we kind of do this interplay of all of these devices in a way that benefits the execution workloads we care about, that a user is expressed, that makes the best use of the hardware platform we have access to. You know, making sure that RDMA works from our FPGA to the given CPU, to a GPU, to an NPU, all of that is something that still needs to be considered in terms of runtime. And then, you know, how do we make sure that custom ASICs all, you know, fit into the bill here for anything else that isn't encompassing from the above. So I just kind of preface this by saying QC plus HPC or HPC plus QC isn't the way to go. Oop, the light turned off. We think, like, obviously the co-design approach is the only thing here that makes sense. You know, I think integrating one of these large scale systems with a platform that is, you know, dragged and dropped into the HPC center isn't really going to make much sense in the long run. We need to be designing these things top to bottom, bottom to top, with compilation in there and with interoperability built in. You know, loose coupling here is a problem. And we don't want to make sure that we're putting APIs in place until the hardware and the requirements for what workloads we care about are actually defined. We think it's a little bit premature in that regard. So loosely coupled systems aren't the answer. We need this full stack approach. And, you know, the idea here is attaching a QC to a HPC system, we don't really think is the way to do this. We think that everything has to be built with interoperability and workloads in mind before one starts designing APIs, right? So quantum offloading isn't really it. It's not an accelerator. It's a full system, right? And this is the kind of the main takeaway here, that we don't see it as a device to execute things that, you know, are part of another program. It is executing the full program itself. FTQC programs are implicitly hybrid. So you have the classical in there, you have the branching, you have the loops, you have all of the pieces necessary, and that has to run within the platform itself. You know, treating the classical and quantum parts independently will limit the overall applications that you can run on these things. You know, and as we're working on defining what these, you know, fault tolerant and even utility scale applications are, one needs to be aware, you know, of the mind that this is an absolutely essential part of what we're compiling, what we're running, how we're running it. It needs to be tightly brought in together. So what I'm just kind of going to say here is don't try to impose API or specs on hardware makers right now. You know, we start with something that works, we will run from there. You know, if you look at something like QIR, which has gone stale because the maintainers have migrated so much over the years, you know, this is a perfect example of why premature standardization is an issue in the community. And, you know, it's too early for this overall. You know, we treat each machine as a bespoke machine. Like I picked the example of the LCLS2, which is kind of the linear coherent light source, if I'm remembering my history correctly. You know, this is a machine that gets built in a field somewhere, and we build custom software stacks around how to use it. You know, and each quantum machine really is at the same level of this. Okay, so my last slide here is kind of outstanding challenges kind of we see coming ahead. Compilation as a bottleneck is something that we need to be aware of, that this is something that should be brought into mind as we're building out these systems, that compiling top to bottom is absolutely essential. We want to make sure that all payloads and interoperability has to happen between CPUs, GPUs, MPUs, FPGAs, the QPU, whatever you want to call it, whatever lives on your ultra-fast bus, your fast bus, and your slower buses that live somewhere else. These things need to be all compiled for and brought in together within the same stack. We need to figure out how do we do the interoperability. What do we do for RDMA? How do we do approximately 1 microsecond, peer-to-peer communication? How do we make sure that the FPGAs talk to the hardware? All of this still needs to be defined. More importantly than anything, though, maintaining an open ecosystem that we can all build in. We're 100% behind that. Everything we build is out in the open. We want to make sure that everything is designed and spec'd in the wild so that you can kind of see what's going on. Feel free to have a look at any of the open issues and PRs as we're building it out. But the main thing I think to take away is organizational overheads here will slow everything down for everybody. Premature standardization, as we kind of said, is going to cause issues. We should just let people figure out what they need to do to build things and get out of their way. Once we have a working software, hardware, co-designed ecosystem, great. We should standardize it at that point. So that's it from me. I hopefully didn't say anything that's too scary for anybody. I'm happy to take any questions or comments, or feel free to discuss further. I am aware it is now 12:44 and I have the meeting room for another 15 minutes, so I'm happy to answer a few questions until then.